So no need to specify value of resistors, just what are positive and negative resistors, that's enough. Okay. You just derive value of K, that's enough, right? Okay, so it was simple. I just simplified one of the examples of Ken Martin book. It's same thing. Just I simplified, removed two capacitors. As you notice, we have only Z equal to 1, which is equivalent to S equal to 0, right? So therefore, two capacitors have been removed from input. That's why you don't see those two. There is a 0 at S equal to 0. That's it. It's a bandpass filter. So then it is just, everything is given, right? So it was a straightforward. So just it's a simplification. So and because values are given, you just start from K4. I just write it here. So B0, for example, is 1.9 and B1 is minus 1.6. So this will be 0.3. So K4 will be square root of 0.3 and then you replace, therefore you will get K6 and K2. Keep it, I don't accept after starting solution. And then, yeah, where? K6 is 1 minus P0, P0 is 0.9. Okay, yeah, sorry, 0.1. Okay, so it will be 1 upon 3. 1 upon. Okay, we don't know this. Okay, so just 10 square root point. And then from here, so we know K4, then K2. So A0 is here, minus A0. So this minus is here. A0 is minus 0.3, so it will be plus 0.3. Okay, I thought it is A0 upon K4, and K4 is square root 0.3. So it will be square root 0.3. So knowing that, then I didn't give any value for C1 and C2, then you can just assume something and then get it. The main part was to determine value of K. Okay, so the whole point was to be familiar with this architecture. So that's why I ask you draw equivalent schematic in continuous time domain. If you draw, this part and this part will be replaced by resistor. So you will see that it will be a bandpass filter. So this is equivalent circuit, only the question was which resistor is negative. As you can notice, this is positive, this is negative, right? Look at the phases. So this is our positive. So if you remember, once I asked you, what is the use of you having forwardular approximation is to implement a negative resistor. So two things have been removed. One resistor which was parallel to this capacitor and one capacitor which was between this node and input node. These two creates two zeros. Those two zeros have been removed. Therefore, here your HS also will be something like this. And S equal to 0 means a 0 at S equal to 0, right? This will be translated to a 0 as Z equal to 1. Okay, which is a bandpass filter. So this is the simple biquad. Okay, I noticed many of you have derived it and also have done more. Like for example, drawing signal flow graph. Okay, fine. So main concepts of switch capacitors filters are covered in this few lectures. Few things are left that I will tell you. One is related to effect of non-idealities in op-amp. So this is an old paper, however, it is from Ken Martin. I think it is when he was a student, and with Cedra. So you will see the how he has explored the effect of finite gain and bandwidth of the op-amp. Because time is short, I don't cover it, look at it, and I don't explore it in this lecture. However, you read it, and then if you have any question, because specifically it is an old paper, then it will be very easy for you to read it. If you notice, for example, if you look at papers which are published 30 years ago, then reading them is very easy because they look like a textbook now for you. So concepts are very well understood. So, and the main point is that the same thing that we have in continuous time domain. If you have a finite bandwidth, if you have a finite gain, therefore you replace gain of op-amp by say A0 upon 1 plus S upon P, right? So it has its own transfer function. And therefore now you will have a new transfer function which will include op-amp gain as well as dominant pole of the op-amp, and then proceed. Now see what will be the effects. And he has several plots according to the bandwidth of op-amp and gain of op-amp as a parameter, which shows that how the characteristics of the filter get distorted because of these non-idealities. And then actually those plots gives you a good reference and benchmark plots when you want to design for a particular characteristics. How much distortion you are allowed to have even in the stop band. But I don't enter into that because then we will face shortage of time in data converters. So that's why I start data converters today. So the whole concept behind switch capacitors was that we will get rid of the problems with process variations. We will have a very nice, in fact, programming capability also. And everything is controlled by ratio of capacitors. Of course, by changing sampling frequency, specifically increasing oversampling ratio, which is ratio of sampling frequency to the maximum signal frequency, you will be able to get better approximation of omega t much less than 1. T was of 1 upon Fs sampling frequency. So this is one point, and another point is that if you want, everything also is controlled by ratio of capacitors and sampling frequency. Therefore, if you keep ratio of capacitors constant and change sampling frequency, your filter characteristics will be scaled accordingly. So this is the overall view, and then one was what about this frequency wrapping, and that was because we are never able to make this omega t much less than 1 approximation valid. Therefore, we should be careful when we are converting from continuous time to discrete time, and we should be careful, like whatever characteristics we have in continuous time, we cannot expect in the discrete time. Therefore, it would be better to have this frequency wrapping. So first we consider this, what are our required characteristics. I gave you one example in the frequency domain, discrete time domain, frequency characteristics, wrap it into analog domain, continuous time domain, and then bring it back by using one of the transforms that we learned, and preferably bilinear, and then you will get the new values of poles and zeros for Hz. So this was a very standard format or flow for design. Okay, so you have Hz. In fact, you don't have Hz, you have characteristics of the filter in omega domain. Omega is the digital frequency domain. Then you will wrap it into continuous time domain. You will get new value. You will get the corresponding analog values, analog frequency values, or continuous time frequency values. Bring it back to digital domain using one of these rational transformations that we had, preferably bilinear, and then you proceed now by realizing Hz. So this whole process is valid for any number, and then we came with this by quads, and then they are also standard values, and then examples also are given in the Ken Martin book, as well as in Schumann book, as well as in Cypress application note. So you have 3 references which have enough number of examples, but the whole procedure is same for every order. Okay. So now we start today about data converters. So I don't talk about what is the importance of data converters. Everybody knows. So just we jump to the main concept. So eventually main concept is, I have an input signal. This input signal is an analog signal, okay? And I want to do digital processing, therefore I need to convert it to a set of digital codes. So therefore that is what ADC does. However, to convert it, I cannot do it continuously. Means that I cannot have a signal which is continuously changing with time. It's very difficult to digitize it, because when do you want to digitize it? Just continuously you want to take one by one value of signal, but how deeply into time you want to go? It is not possible. Every 1 nanosecond, every 1 picosecond, every 1 femtosecond, which is not possible. Therefore, here, exactly like switched capacitor filters, we need first of all to have samples of the signal, and then give it to data converter. So therefore, sampling applies here as well. Therefore, we need to have samples of the signal. Again, because we have samples, again the concept of aliasing is applicable here as well. So till this point means that aliasing and sampling, everything is just as switched capacitor circuits. However, in switched capacitor circuits, we analyze everything in continuous time domain, in discrete time domain, but analog amplitude. Now what we want to do is that not only to make it discrete time, but also discrete amplitude. In other words, now we want to look at a set of quantized values for the signal, not analog values. Means that now not only time is discretized, but also amplitude also is discretized. So in fact, data converter in one step beyond switched capacitor or discrete time processing. So here therefore, the amplitude and time both are discretized. So, however, working with quantized values in an amplitude domain, say voltage domain or current domain, also is not so easy. Therefore, because otherwise you will need a multi-valued logic. If you have, for example, 16 quantized level, you need a 16 level logic. And when you have a 16 level logic, then means that it is very difficult to control noise. The whole idea behind going from analog to digital domain is to have freedom with respect to noise. The noise is one of the problems in analog domain. So in digital domain, you are trying to improve noise margin by discretizing the amplitude. However, if you have 2 levels, we will have better noise margin. If you have 4 levels, your noise margin will reduce at least by a factor of half. And then if you have 8 levels, again it will reduce by more, again another factor of half, and so on. So therefore, we want not only have quantized levels, but also we want to convert them into a maximum, I would say that at least at these examples that we cover, 2-level logic. Your 2-level digital code or 2-level binaries means that only 0 and 1. You may have 4. But at least what we cover here will be 2 bits, 2 levels, means that only 0 and 1. So therefore, what we want is that we have now a 2-level, this minimum level in fact, 2 levels logic, and then we want to logic levels, and then we want to convert these quantized levels into those 2 levels, means that either 0 or 1. However, if you want to do that, then we lose a lot of information. You have, how you can just convert, say for example, 16 quantized levels just into 0 and 1. It's very, in fact, inefficient. You will lose the entire information. How to avoid it? Therefore, we need to increase number of bits, or in other words, we need to increase the number of symbols which represent information. Therefore, we are not going only with one symbol or one bit which represents 0 and 1, but also a number of them. That is the reason we need to go with more number of bits so that we would be able to cover more number of quantized levels. So this is the whole idea. Therefore, we need to have sampling frequency, means that we need to sample the signal. So input of this module is some sampling clock. Input signal is completely analog, continuous time, continuous amplitude, but inside ADC here, in fact inside ADC we will have a sample and hold or track and hold circuit. We need to have a reference level because after all, when we are doing quantization, we are dividing the signal levels into n number of levels. So therefore, we need to have a reference. So accordingly, we would be able to do this quantization. And then finally, we will generate n number of bits, and each one of them will have a 2-level binary value. So this is what a data converter does. However, you may have 4 levels as I said, therefore that will be a different scenario, but here we will cover only 2 levels. So therefore, suppose if you have a sine wave, just starting with a simple sine wave, 5 kilohertz sine wave. So you sample it with a frequency of 100 kilohertz, and you can do this simulation easily in MATLAB. Some of you may have done it before. Just it's a simple example, like these are now samples of the signal, and then we will go to frequency domain. You can plot in frequency domain. As you can see, you will see the alpha. Of course, this is discrete Fourier transform in MATLAB. So it shows you what are the main harmonics of the signal. Here, the only visible thing will be this 5 kilohertz because there is no other component over here. So it will show you only this 100 kilohertz in between, and then plus minus 5 kilohertz. So this is just a simple this is something that you know from switched capacitor theory. But one thing which is very important here is when we are talking about quantized levels, because in switched capacitor circuits we didn't talk about quantized. That concept was not there. But because now here we are entering into quantization, then we need to be clear what will happen right from the beginning. If I quantize values before going to digitization, just quantizing values, how much information I lose from signal, okay? Once we lose some information because of discretization in time domain, which is sampling. Now we will lose more information because now we have one more step, which is quantization. So therefore here we have actually more loss of information compared to switched capacitor circuits. Before talking about codes and quantization and digitization, we should explore this quantization with more details. So for example, so therefore you have track and hold, you have anti-aliasing filter, your sampling rate should be above Nyquist rate. These things will be same as before. However, now we need to quantize the signal. What do we mean from quantization? So I have just signal, right? So for example, X, right? So it is versus, value, say versus V, voltage. It can be current also. Whatever signal we have, at least electrical signals. And here we have some quantization levels, okay? Or quantized amplitude. So these quantized levels also are mentioned versus volt. So my signal, suppose for example, changes from some value from 0 and Fs. Fs is used a lot in data converter literature, which is full scale. Is that mean value, max value of the signal, which is called a full scale for the signal. So now I want to say, for example, introduce 4 quantized level in this 4 value in this domain. So I divide it into 4 parts. So here this means that now I have these 4 quantized levels. Now if signal is between 0 and this value, I can show it by 0. If the signal between these 2 levels, then I will go to the next quantized level. This is one way, okay. So in fact now I am looking at all signals in this range only to be equal to Fs by 4. And then Fs by 2. So if my signal is between Fs by 4 and Fs by 2, it will be mapped only on Fs by 4. If it is between Fs by 2 and 3 Fs by 4, it will be mapped on Fs by 2. And finally, if it is between 3 Fs by 4 and Fs, it will be mapped on 3 Fs by 4. Okay, so another way would be So same thing, I'm plotting same diagram now by just changing my levels. I consider if my signal is fitting Fs by 8 from quantized level, then it is considered to be Fs by 4. Therefore, I will have just a change. It's just like a change in the gain. So now this was 0. This is eventually Fs by 8. And this is Fs by 8 plus Fs by 4, which will be 3 Fs by 8. And this is Fs by 4. Now what we say, this actually is better. We say that if my signal is Fs by 4 or plus minus some delta around Fs by 4, I map it on Fs by 4. And of course here I should say that, okay, if my signal is around 0 plus minus Fs by 8, right, full scale by 8. But I have considered I don't have negative signals, therefore I don't go below 0. And then you will have Fs by 2. Essentially this quantized levels will be intermediate points now. Fs by 2. Okay, so just I'm mapping. I don't write anymore. So okay, so this is Fs by 2. And then you can proceed as I'm doing. Again, middle point here. So therefore this point now will be Fs by 2 plus Fs by 8, which will be 5 Fs by 8. And this is Fs by 2. And that is 3 Fs by 4. Okay. So because in textbooks you may see any one of these two. I'm just explaining what is the difference between them. The second one is better. As I said, the reason is because your quantization level is in between. Means that you will have plus minus for every quantization level QV. You will have plus minus full scale by 8. Variation in the amplitude. So what does it mean? Means that here we are losing information. So if I increase number of quantized levels, this is one way to reduce amount of, in fact, distortion which is generated in the signal.
If I use the second diagram,
yeah.
Fs minus Fs by 8
value. Yeah, that is correct. Means that practically actually we should have this, right? Here only for the range which is around 0, you will not have. The reason is because practically we consider my signal is between 0 and Fs. But if my signal is not between 0 and Fs, suppose if I have a fully differential signal which can take negative values, then actually I will go from minus Fs to plus Fs, and then I can cover this perfectly.
For differential, this is preferable, and you have only positive signals and above.
No, I don't think even for the above, for positive signals, the above one is preferable, because what happens is that your quantized level is exactly your threshold level. And this means that if you have a little error around Fs by 4, your code will change. Because you will see, if you are at the right side, you will go to the next level. If you are left side, you will go to the one level before. You don't give enough margin for negative noise. Instead, you are increasing positive noise margin. So it's better to have equal positive and negative noise margin. That's why even for positive signals, second one is preferred. No, actually this is Fs. Maybe this is Fs. So here this is 5 Fs by 8, and then this is 3 Fs by 4, and finally this is 7 Fs by 8. So it will stop here. Means that, see, exactly why this is happening, because at the 0 side I have lost this, right? Here I have one more, in fact, interval or more headroom for positive noise only at the last level. But usually we don't go, in fact, to the exact perfectly full scale. We prefer always signal also to be below full scale. Because at vicinity of a full scale, we have a lot of problem with the comparator. So we prefer to be, comparator cannot have resolution of 0 volt. Therefore, it's better always to be below full scale. Okay, so then, after all, either we use the above. So see, right now I have not entered into any code generation. Just we are talking about a process which is called quantization, which is required before generating codes. Of course, here we are talking about uniform quantization and then static quantization. Now, for example, if you have information about signal, you may have dynamic quantization. Quantized levels may not be same. Even your sampling frequency can change. System can be adaptive. So these are advanced versions of data conversion systems which are used nowadays. But here first we start with the formal, static, uniform quantization levels. Okay, so then now, if I plot noise versus, in fact, I should call it quantization noise. Sometimes they call it quantization error. So what does it mean? Means that both are correct. Eventually now we have quantization error. Means that when I sample from my signal and give it to switch cap, that is perfect because that signal is there. But now I'm quantizing it. So therefore I'm creating manually, artificially an error in the signal. So that is called quantization error. And quantization error is difference between the signal level that I have here and the quantized level which now assigned to the signal. Right? So that is the error. So therefore, quantization error QE is equal to signal level, real signal V minus VQ. So V is the real value of the signal which is held on the capacitor or any storage element ideally, and then VQ is the new value of new quantized value which is assigned to V. V is not V anymore, now it is known as VQ in this system. So see, quantization is not an explicit process. Eventually it happens implicitly. When you convert an analog signal to a digital signal, implicitly you do quantization. But if you look at the data converter architecture, you don't see any module which is called quantizer. I mean, it is a virtual module. Inherently inside converter, because you don't do that, you don't quantize. What you are doing, you are sampling the signal, for example, compare it with a reference value, generating a bit, right, at the output of comparator. There is no quantization process here. However, implicitly quantization happens, because when you are comparing a signal with a reference value, it doesn't matter whether the signal is 1 millivolt above that reference value or 2 millivolt above that reference value or 3 millivolt. Everything looks like VREF. A little above VREF, a little below VREF. Therefore, it is like that you have mapped all signal values to a single value of VREF plus epsilon or VREF minus epsilon. Because any value other than that still is equivalent with the same. Effect is same. So you have a function, instead of to be a function of V, it's a function of VQ. Okay, so that function is comparator. So comparator eventually maps your signal on a quantized level, but inherently, not explicitly. So we don't quantize and then digitize. We digitize, but quantization happens during digitization. So that is also one concept. So now, therefore, we see, okay, how this quantization error will be. So just, we continue with the same. Okay, here I had decided, for example, to divide it to 4 segments. You can divide it into 8 segments, 16 segments, and so on. Because we are talking about only 2-level logic and therefore binary values, therefore automatically we are talking in base n, 2 only. Okay, so then therefore again still I will have my signal. Now the best thing would be, because full scale is something which depends on your technology, it depends on your circuit, therefore it depends what is your maximum supply and other issues, it's better to always normalize it, because if you write V upon full scale, then you have a normalized, just normalized numbers. Okay, so looking at the second plot, which gives plus minus, equal negative and positive noise margins for the signal value, or in fact variation for the signal value. So if signal is 0, then quantized level will be 0, that is correct. But as I increase signal level, my quantization error increases, right? So therefore we would expect to have something like this. Suppose if this is Fs by 8, you will have a line, right, which is increasing in the amplitude, starting from 0. So this is quantization error. Now you reach to Fs by 8, okay, then your value jumps to Fs by 4. However, if your input value is Fs by 4, your output value is correct. But for values between Fs by 8 and Fs by 4, your signal is less than your quantized level. Therefore, you have negative error, right? Therefore, you have a jump over here. I just show it in this way. Amplitude is not correct, but just to get rid of this Fs by 8. So now, at Fs by 4, it is correct, and then you will have again positive values. Again this will repeat. So practically, of course, this figure should be like this. It is symmetric. So this is input signal normalized to full scale. This is quantization error. this is 0, and these are your quantized levels, whatever they are. And if you notice, maximum error will happen at these edges. So here, for example, you have Fs by 8 and here you have Fs by 4. Therefore, difference will be Fs by 8. And the same thing will happen here. This is 3 Fs by 8, this is Fs by 4. Again, difference will be Fs by 8. But one is positive, one is negative. And difference is 2 Fs by 8. Therefore, eventually is, suppose if this is your delta V, okay, this is your step size or quantization steps. This is also delta V in general. Okay, for uniform quantization. So for uniform quantization, so quantization error in general obeys this pattern as a function of input signal. So therefore, this delta V is your segment size. For one quantization level. And in fact, your quantized levels for signal is delta V. For quantized levels also, if you notice every quantized level, difference between two consecutive quantized levels is here, for example. This is Fs by 4, which is same as segment size, Fs by 4. Just an example. And your error also will be same as this. So it will be delta V by 2 minus delta V by 2 maximum. Okay. Sometimes this is called quantization step. I mean, you may just see. Okay, so therefore, because this process is a process which includes error in the signal, then it's better right from the beginning to be clear how much error it generates. Okay. And because we are dealing with finally we want to convert these levels to codes which are essentially binary codes. That's why here we usually consider 2 to the power n, and n is the number of bits. Therefore, when we want to generate this delta V or segment values, we always use this full scale divided by 2 to the power n. So means that the segment size always is a full scale divided by a power of 2, because we are dealing with binary codes. So in other words, if I use n number of bits, I will be able to cover 2 to the power n levels, right? So that is correct. So eventually if you generate 2 to the power n levels, quantization levels, then this means that you can cover it with n bits because it's binary, power 2. Okay, so these are some introduction. Now therefore the first part is how this error is characterized. So right now it's just a first step. Therefore we need to see how much error is generated. So look at this error as a noise. You can look at this error as a noise. Suppose some noise is added to the signal in such a way its value has changed, and always it changes the value in such a way it will be one of these quantized levels. So therefore the first in fact figure of merit that we talk about it is SNR, signal to noise ratio. So we could call it signal to error ratio, that is also correct, but in literature it is called signal to noise ratio because afterwards other sources of noise and quantization error are clapped into one complete noise source. But of course they are not of the same nature. For example, thermal noise is random noise, but quantization noise always is not random. So it's random only if your signal is very active, in the sense that it can get all values over a long time with a uniform distribution. Therefore actually you will get a completely close to a random quantization error, which will be eventually a random noise. But therefore this is not exactly same. However, in this analysis we assume it is, so that you would be able just to simplify it. So what is signal to noise ratio? Essentially signal power divided by noise power. And here we assume at the first step we are talking about only quantization error. So how much, if eventually it is equivalent by adding noise to the signal. So how much it is added? So first of all, just to review, like for example if you have a sine wave, with a frequency omega 0, so average of this sine wave is equal to 0 in time domain. However, this signal has some power level. To be able to measure it, therefore one criteria is, because it's periodic, to look at average power. Therefore average power is defined as average value of signal square if we normalize it to and consider resistance is equal to 1 ohm. So if you apply this signal across a resistor with the value of 1 ohm, average of this value will be the amount of average power which is dissipated in the resistor in one cycle. So this is definition of average power. And then you also know that this will be a square by 2, right? Okay, so RMS value of signal eventually is the effective value of a signal which could generate same power equivalent with this power, average power, if it is a constant value over time. So similarly for noise also we can define RMS value of noise, and therefore we can measure signal to noise ratio by measuring the signal power, average power of the signal divided by average power of noise, or RMS value of signal divided by RMS value of noise. So therefore now, because we know that we have an idea of the signal quantization error, therefore we would be able to calculate RMS value of noise, quantization noise. How do we do that? So eventually quantization error was like that, so we calculated. So quantization error is like that, right? Just I get one segment. This was segment size. For binary, for example, it was full scale divided by 2 to the power n, and eventually it was delta V. And this side was delta V by 2. This is also delta V by 2. So, as a function of input signal, this quantization error was a periodic signal, right? As a function of course, input signal. V upon, okay, yeah. So, therefore, we assume, suppose your signal is completely active in the sense that if you look at it at a time domain, it will take all values with a uniform constant distribution. Means that the probability of having a value between 1.1 and 1.2 is the same as probability of having a value between 1.2 and 1.3, and so on. Therefore, signal will have all values with a uniform distribution. So, if this is the case, then means that because then I want to have some approximation to be able to calculate RMS value of quantization error. Because if it is not, then it is dependent on the signal. Then, in fact, I cannot calculate RMS value of quantization error independent of the signal. We just make this assumption to be able to calculate QE as an independent function of V. VT, in fact, not V, VT.
This distribution is possible to get from hardware also.
Yeah, you mean that extract signal distribution in real time? Yeah, that is possible. I mean, actually in recent data converters, what they do, it's exactly this. They use, in fact, they extract the statistics of the signal, and then according to that, they look at how this quantization error changes. And then according to that, they adjust this quantization levels. It is completely dynamic and adaptive. So that is something that definitely, I mean, has a scope, and nowadays, I mean, it is used a lot. Because you can even control sampling rate, even sometimes you can come below Nyquist rate, having statistical information available. Yeah, this, I mean, practically is that is in fact better. Only it needs a lot of, hardware overhead, because you need memory, you need this sampling, you need to store this data, and then you need to use this sample. In fact, there will be a GSP processor usually on top of this system, which will control data converter itself. But it is used because when signal has a lot of dynamics, then using a uniform quantization, uniform sampling rate, everything now is waste of resources. And it's very difficult also to design a comparator which will have a resolution of say 26 bits with a sampling rate of 2 gigasample. It's not practical. However, if you have statistics available, you can actually adjust. So then your resources also will be used properly. You don't need to make it a general purpose data converter. You can make it a special purpose with adaptation. So, but right now here we consider it is general, okay, and then signal can get any values, therefore signal is quite active. Eventually assumption is, in this analysis, is active signal. So active signal is a signal, if you look at it at time domain, it will look like noise, eventually. It will look like noise. It can get any value and completely with a uniform distribution. In fact, it will be very close to a noise type of signal. Okay, so therefore now we calculate RMS value of noise or average value of quantization error. So we look at one cycle as a function of input. So therefore we get average over this range. So it will change, for example, if this is the middle value, I mean any value you can consider some reference level, right? So this doesn't matter. So I call it V0 because then it makes it quite general. So this will be V0 minus V upon 2 and then V0 plus V upon 2, and this is just a line, right? And this line crosses V0. Therefore, we need to write equation for this line. So at V equal to 0, it is 0. In general. And then this is the slope of line M is equal to delta V by 2 divided by delta V, therefore it is 1 upon 2. So just we replace it here. This should be delta V. So you calculate this. One thing also you can easily consider, like V0 is 0 for simplicity, and then therefore it will make it very easy. Finally the value you will get, just you do it. Okay, and therefore RMS value will be square root delta V upon square root 12. Okay, so I stop it here, but at least now we have derived by considering signal is very active, we have derived an idea of what is the average power in this noise, if we call it noise, because then it will be noise. If signal is very active, signal itself is like a noise, and noise minus these values, reference values itself will be noise. Therefore now we have RMS value of noise. So what is important? Only to have RMS value of signal, and then ratio of them will give us an idea of the SNR for this quantization process, which is happening right for any sort of data converter. By the way, there is one point Yaman referred. If you look at lecture, I think 9, there is a mistake in the example, just you correct it. In lecture 9, here, Z is equal to e to the power j2 pi. Okay, we assume that if this assumption is correct, then Z will be almost j2 pi. This actually should be plus 1, right? Z is e to the power j2.2 pi, so it should be 1 plus. It is close to 1, not close to 0. Z is equal to, mapping will be on the unit circle. So here this cosine 0.2 pi has been omitted, so therefore this term should be added. In fact, if you want to be more precise, you can write it cosine 0.2 pi. So therefore everywhere you need to correct it. Here, everywhere that you have Z, and here. So this to be corrected. So correct this, and to be more precise, you can even include, in fact exactly you write sine and cosine. You can use, in fact, Z is equal to j sine 0.2 pi plus cosine 0.2 pi. So this is correction. Okay. Okay, only calculator.